Exercise 51. Let's talk about this exterior power of R module M. So R be a ring, it's a unitary ring. M R module. So let's first recall. If k bigger or equal to 1, it's an integer. The case exterior power of M denoted gamma k M is the R module. M tensor product with itself, k times quotient by submodule, that's denoted by j small k, where this j small k equals 0 for k equals 1, and the submodule spanned by M1 tensor M2 tensor MK with MI equal MJ for some different from J. So this is one way. So this is when k equals 1 and jk equals 1k bigger or equal than 2. This is one way to define this exterior power using tensor product, quotient tensor product. Okay. So, a notation for M1, M2, MK elements of this R module M. The coset of the crest of this tensor product in the quotient is denoted by wedge. By convention, we set gamma 0 to be just this coefficient ring R. So this J0 would be 0 in so this quotient is trivial quotient because M tensor 0. We also by convention set it to be R. So we are following this lecture notes by Konar. And the exercise proved that for M R module and N R module, prove the following fact. So could be think of as universal property of exterior power. Let F from K M to the power K to N be an alternating multilinear map And where k is bigger or equal than 1, there is a unique linear map denoted by f2 from this exterior power of m to n such that we have commutative diagram. And it's commutative. In other words, f2 and one wedge m2 the same as f m1 m2 mk. So proof. Firstly, when k equals 1, this is just m f to n, and here wedge is just the identity map, and to gamma 0 m, which is again m. And so we have this f2 which is just defined to be the same as f so when k is bigger or equal than 2, so by the universal property of tensor products, we have a multilinear map from mk to n, and so it's factorized through the tensor product. So we have this factorization to m tensor k. So this is map is the tensor. So here it's the map that maps m1 m to mn, map it to the wedge, right? And here it corresponds to the tensor product. This is canonical map, and so I factorize so under our assumption, we just have to show that this further factors through the quotient of this tensor product, because by our definition this is the quotient by gk. And here is alternating, not only multilinear but alternating. That's why it factorizes. So f, right here, f is alternating, and so it vanishes at any key tuples such that by the same condition as how we quotient as a module, vanish at those key tuples such that mi equals mj for some I different from j. And thus this linear map here we induced further factorize because it vanishes. Let's call this f2 1. So f tilde 1 vanishes at all those M1 tensor MK such that Mi equals Mj for some I different from J. And so this further vanishes on some module, and so it factorizes through its quotient. Which is what we call JK, and so this is, by our definition, what is our exterior power. And this is how we define our F tilde, and this uniquely defines F tilde because this is uniquely defined as, so they give you generating set this spans so let me put a remark. So why we use this quotient of tensor product to define this exterior powers? So we could define differently. So very intuitive way to define that, maybe also very common way, would be just consider it as alternating multilinear functions. So I take an example. So for example, let's define this. So here I mean the du space of Rn. So all the linear maps from Rn to R, the linear. And so what we are doing is we want to define this to be, so think of this as our M, right? So we're going to define this to be the vector space. The vector space of all the alternating multilinear functions of what? So there K means K vectors in Rn. So put it more transparently, I mean consists of all those alternating multilinear functions from the product of Rn K times to R. And actually, so of course this the definition coincides because multilinear corresponds to tensor product, and then alternating is quotient. So let's look at this as an example. So sub exercise. So this vector space has basis. Let's talk about the generating set. of the following form. Let's call it d x I, where this I is a couple of index, let's say some I1, I2 increasing. So ik bigger or equal or maybe put it some I1, I2, ik integer such that they're bigger or equal to 1 and they're increasing. So where this dxi is defined as follows, so we have to define it as alternating multilinear function. So it is that given, let's say, k vectors, right? So with 1, with 2, with k, how it is defined to be, look at this column matrix with 1, with 2, with k. So this is in particular n by k matrix, right? What I want to say is that we want to compute the determinant, but this doesn't make sense at this moment because it's not square even. What I'm going to do, I'm going to pick the I1's row, I2's row, etc. until ik's row. By doing that, you're picking out a k by k submatrix, and you compute the determinant of that. It gives you a real number. I want to show that this actually form a basis. In particular, as a corollary, this tells you that the cardinality of the basis is basically C and K. Okay, and so thirdly, let's take one example. So when this K equals n, what we're talking about here is comma n r n star. So this would be one dimensional because this is 1, and that basis, basically this x1, 2, 3, 4, n, this is exactly the one which maps given n vectors to its determinant, because you're picking all the n rows. So the determinant, so maybe it's more correct to write this acting on this Cartesian product and determinant of the corresponding matrix. Right, this is cool. Think about it as an example.